Last time we introduced the variation of temperature with time for the solidification of a pure metal. Now we'll consider the case for an alloy. For an alloy, the behavior is a little bit different because we have two different melting temperatures. So for example, if you take the following diagram, it represents the variation of temperature with time during solidification of an alloy of nickel and the copper. Okay, and as you can see here, we can observe always variation in temperature. We don't have a phase of constant temperature because we have two melting temperatures, one for copper, one for nickel, and they are different. This will cause, if you want, continuous variation of temperature during the solidification process. Now, how we can make the analysis of these graphs? To start with, you have the following graph that shows you, depending on the temperature, what is, if you want, the depending on the constitution of your alloy. So you know that the percentage of nickel can vary. This will change the composition of the alloy. So for each percentage nickel copper, you will have a different range of temperatures where you can consider that freezing will begin. And for example, if I tell you I give you an alloy of 50% nickel, 50% copper, you come to this graph here and you just take for a 50% composition, what is the corresponding value of? So if you read here, you will have two temperatures of intersection with this line. These two temperatures will give you the beginning temperature for freezing and the temperature to complete the freezing procedure. And these temperatures will vary according to the composition. So, for example, here for this case, we consider that the freezing will start at this temperature, and it will end at this one. Now, if you go to the graph of solidification, you have first, as usual, you start with the pouring temperature. In the first phase, you have liquid cooling. And as you can see, freezing, you can detect freezing by the sudden change in slope. It's true that when you have an alloy, you don't have a phase of constant temperature, but the change of slope will mark the beginning of freezing, because in the liquid cooling process, the decrease of temperature with time is much faster, while during, if you want change of phase, when we go from liquid to solid, the slope of variation of temperature will be reduced, and it will take a linear profile. And then it will be marked by two temperatures depending on the composition of your alloy. So we can consider that here freezing will begin and here freezing will be completed. So at this point, the constitution was 0% solid and 100% liquid, while at the end, when freezing is completed, you have 100% solid and 0% liquid. So here we have switch in percentages completely, and any point in between will be a mixture of solid and liquid. And finally, at this point, when you have 100% solid, you have the solidification is complete, and now you, for the remaining time, you have cooling of your solid. And again, this transition is marked by now a fast increase in slope. So whenever you move from the change of phase to the cooling, the rate of change of temperature will be much faster. Okay. Now we can identify the total solidification time as the time from beginning, if you want, from the pouring time until the complete freezing. This is the total solidification time, and this is what we call the local solidification time, where you have change in phase.
Okay.
Yes?
I didn't understand what happens to the slope. Can you please repeat that?
Sorry, I cannot hear you well. Can you try to raise your voice, please? Can you repeat, please? I cannot hear you. Or if you want, you can type your question in the chat. Now, we have already seen the solidification behavior of a pure metal. Okay, the slope is lower during the change of phase. So here, if you look at the slope variation, during liquid cooling, okay, you can detect high slopes of decrease of temperature. Okay, suddenly when you start to have change of phase, your slope is much smaller in absolute value. Okay, this is because during phase change, you have the heat form is more absorbed in order, yani if it's a pure metal, it will just be absorbed at latent heat. Okay, and this will lead, if you want to change of phase. Here, why you have variation of the temperature? Because you have two different melting temperatures, and this is why one part of your alloy, which is, let's say, the one that is characterized by a higher melting temperature, will start to or freezing temperature will start to solidify before the other. This is why during this phase you have a mixing of sensible and latent heat. But already, because there is latent heat, this will decrease the variation of temperature with time. And you can see this with a smaller slope of variation of temperature during this zone, because you have phase change in this case. Now, as you end with your change of phase, so you have 100% solid, and now you continue to cool, you can detect at this point again a faster slope of decrease, because now the exchange is completely in form of sensible heat and not latent heat. Okay, is it clear? Okay. Okay. Now, concerning the behavior of solidification of alloys, it's a little bit also different from a solidification of pure metals. It's true that there is a common behavior near the walls, okay? And also you observe here, if you want, when we are a little bit far from the wall, you see the columnar grains, columnar parts, okay? However, at the center, again, you see formation of grains. And this is due to, if you want, the composition of your alloy and the different melting temperature. Because of the different melting temperatures of the components constituting the alloy, at a certain point, we'll have, again, formation of grains at the center of, if you want, of your cavity. Okay, so this is the characteristic grain structure in an alloy, which is showing segregation of alloying components in the center of casting because of, if you want, the different melting temperatures. So what will happen is that here, in a certain phase of solidification, let's say both were in the liquid state, which will, during solidification, this will help into, if you want, forming a certain part that is of columnar shape. But whenever you will have very, one of the constituent will solidify much before the other, you start to have a variation in the composition, and this sudden variation in the composition will lead to the formation of grains at the center. Now, how to calculate the solidification time? The total solidification time is the time required for a casting to solidify after pouring. And the solidification time depends on several factors. First, it depends on the size and shape of casting by relationships known as Shrovenov's rule. And from this rule, the time of solidification is first proportional to a certain factor, which is called the mold constant. And this depends on the mold we are using, material and geometry, okay? And then for this case, for the molding constant, if we are using same mold, for example, for different processes, or we can consider that CM is the same. Now, for V over A, V is the volume of the casting, and A is the area, surface area of the casting, while N is the exponent with a typical value of 2. Now we'll see how we'll use this relation to know how to design our riser, because we said that in our risers, the molten metal should solidify after the metal into the cavity, because it should continue to supply molten metal in order to avoid the formation of voids and to fill all parts of our cavity. So first, concerning CM, okay, for CM, to have same constant, we have the following condition. You should have the same mold material, you should have same thermal properties of the casting metal, and you should have same, if you want, pouring temperature relative to melting point. So this means that if you are using a certain, even if you change, let's say, the geometry you are producing. So if you want to cast a sphere or to cast a rectangular box, and as long as you are using same mold material and same type of casting metal and same pouring temperature and melting temperature, so this means that you can use the same value of the mold constant. Now, changing the geometry of the object will affect the other factor, which is V over A. V over A is related to the geometry of the part you are casting, and it will change, of course, from one object to the other. So the value of CM for a given casting operation can be based on experimental data from previous operations carried out using the same mold material, same metal and pouring temperature, even though the shape of the part may be quite different. As we said, the shape of the part will affect the second factor, which is V over A in the solidification time expression. Now, what is the information that Shrovenov's rule will tell us? So first, a casting with a higher volume to surface area ratio cools and solidifies more slowly than one with a lower ratio, because higher V over A, we said that it is V over A to the power N times the mold constant. This is the solidification time. So now if we fix this factor, we are using same mold material, same metal of casting, we can vary this factor, V over A. So for objects characterized by high volume to surface area ratio, the solidification time is more slow. This is why when we talked about the riser, I told you that one of the strategies we can control, if you want, the shape of the riser in order to have a solidification time for the riser much larger than the solidification time in the cavity. So for the riser, when you study V over A for your cavity, for your object that you want to produce, you can play with V over A of the riser in order to have a solidification time larger than the product you are casting. And in this way, the riser will solidify after your final product. Now, since mold constants of riser and casting will be equal, so you know that for the riser, we are using the same material of the mold and we are using the same molten metal. This is why for a riser, the main factor of design is V over A. So this is why during the design of the riser, we should ensure that the riser is characterized by a larger volume to area ratio, so that the main casting solidifies before the riser. And this will minimize the effect of shrinkage that we talked about. Now let us see, we talked already about shrinkage during solidification and cooling. Let us have a certain idea about how shrinkage takes place. So this is an example. You have an open mold here. This is the starting level immediately after pouring. So after pouring, you have the molten metal filling your cavity. Now, because of the contraction when you have changed from liquid to solid state, because you know that the density of a solid is larger than the density of the liquid, and because mass is conserved, so you can have reduction in volume. So this is what we call the reduction level due to liquid contraction. And also you have, whenever you observe solidification process, the first part that will solidify is the part that is close to walls. So here you observe initial solidification at mold wall, which will automatically lead to a reduction in the level in your cavity. And if you want to compensate for this, you can, in open mold in general, we don't have risers, but in closed mold we have. So in closed mold, the riser will continuously supply molten metal to fill any voids. So we can see here also, we have a lot of phenomena that are not desired during solidification. So for example, in this case, the first region that will solidify is near the walls. And then solidification will continue towards the center of towards the cavity center. And because of this effects, this will lead sometimes to the formation of shrinkage cavity, because you don't have continuous supply of molten metal to fill voids. You at the end you might end up with certain voids in your system. However, if you were able to supply in a continuous way molten metal, then you can avoid formation of such voids or shrinkage cavity. So reduction in height and formation of shrinkage cavity can be caused by the solidification process. A further reduction in volume is due to the thermal contraction during cooling of the solid metal. So as a first step, you have the reduction in height, because let's say near the walls you have suddenly a fast solidification, which will cause a reduction in the height level. So in a first step, shrinkage will take place in one dimension, because your liquid, you still have a liquid portion that will fill the remaining parts, and this will lead to reduction in height only. Now at the end, when the whole part is in the solid state, and it will continue to cool, then you will have what is called shrinkage, volumetric shrinkage in all directions. So this is called linear shrinkage at the beginning. And at the end, when you have the complete molten metal transformed into solid, you have, during the cooling of solid, you have what we call solid thermal contraction. And solid thermal contraction will take place in 3 dimensions, and we call it volumetric shrinkage. So for solidification shrinkage, it occurs in nearly all metals, because the solid phase has a higher density than the liquid phase. Therefore, solidification will cause a reduction in volume per unit weight of metal. And we have only some exceptions for this. For cast iron with high C content, high carbon content will avoid, if you want, shrinkage effects. In fact, the carbon is characterized by properties in a way that when you go from liquid to solid state, you don't have decrease in volume. This is why adding carbon, okay, in final stage of freezing will cause expansion that will counteract the volumetric decrease associated with phase change. So carbon is behaving different than all other if you want, the majority of materials that we know. for which when we go from liquid to solid, we have contraction. For carbon, no, it's the opposite. This is why introducing certain percentages of carbons at the end of freezing stages can reduce the effect of shrinkage.
Doctor, I have a question about slide 31.
Yes, tell me. Yeah.
ما كتير فهمت shrinkage cavity ليش هيك شكلها انه ليش طلع لنا shrinkage cavity جوات المولد يعني جوات الاليمنت.
اوكي. لانه انت اول شيء عندك مثل a certain parts، يعني هو شو بيحدد البارتس اللي حتعمل solidification قبل التانيين؟ بيكون في heat transfer مع الانفايرمنت. يعني انت هيدا المولد first you have interaction with walls، okay؟ يعني you have possibility of heat loss through walls. فاول زون حتعمل solidification هي هيدا، اوكي؟ والسو عندك هيدي البارت اللي فوق عندها كمان it can release heat to the environment. فمنشان هيك السوليديفيكيشن بتصير in this direction أو in this direction. فإذا وصلت لمحل صار كله يعني solid، اوكي، في part من جوا حتكون فاضية، لأنه already نحن عنا الإفكت of إذا بدك في reduction in volume، يعني في part حتخسرها من الفوليوم. وهيدي البارت بما إنه كل هول البارتس عملوا solidification قبلها، حنوصل لمطرح إنه خلص في زون ما في بقلبها ميتال، وحتكون in general مش يعني حتكون شوي بقلب السيستم، لأنه هوليك البارتس كل البارتس اللي قراب على الوولز هيعملوا solidification أسرع. وكمان هون عندك possibility of heat release with the atmosphere. So بيبقى لك a certain part هي ما كان في metal enough to fill it، وأصلاً هوليك الزونز كانوا أسرع منها، فبيضل في voids بهالدي الزون. Okay.
Okay, Doctor.
هلا we'll see together what are the strategies to avoid this. Now, what are shrinkage allowance? So pattern makers will correct for solidification, shrinkage, and thermal contraction by the first strategy is by making the mold cavity oversized. يعني نحن بنعرف حيصير في shrinkage, so to compensate for this من الأساس بنحط الcavity size larger. Also we'll see that the presence of riser will reduce shrinkage effects. وكمان we should design sometimes several risers to be able to reach if you want critical locations. I will talk about this. So the amount by which mold is made larger relative to final cast sizing is called the pattern shrinkage allowance. So this is to لازم نعمل study to know تقريبا how much will be the shrinkage, so we can compensate for this by using larger size of our cavity. Now, casting dimensions are expressed linearly, so allowances are applied accordingly. يعني when we talk about shrinkage هلا نحن حنشوف إنه في linear shrinkage في volumetric shrinkage. We'll talk about the difference. بس in general بس نحكي dimension نحكي بكل direction. So in this direction we'll have shrinkage of this percentage, in this direction we'll have shrinkage of that percentage, etc. Now, to minimize the effects of shrinkage, it is desirable for regions of the casting that are most distant from the liquid metal supply to freeze first, and for solidification to progress from these regions towards the riser. And if you can create what we call directional solidification, we'll be able to get rid of voids. شو هي الidea? The idea is that for example, if you have a closed mold, the regions that if you want will be very far from يعني extreme regions هن more critical one، لأنه you might have any blocking effects ما يخلي المولتن metal بقى يوصلون. This is why in general when we design risers بنحطهم بطريقة إنه to supply first molten metal to these regions. فنقدر نعمل لهم solidification if you want before other parts. يعني مفروض نقدر، لأنه إذا انعمل solidification ل other part before حيصير في blocking effect، ما بيقعد المولتن metal يقدر يوصل. So the freezer should be close to such critical locations to be able to supply them with the required molten metal. In this way, molten metal is continuously available from risers to prevent shrinkage voids. And this is what we call directional solidification, which describes this aspect of freezing and methods by which we can control the solidification procedure. Now, how we achieve directional solidification? So to achieve it, first we should apply Shrovinov's rule to design the casting, its orientation in the mold, and the riser system that will feed it. So we should be aware, if you want, sometimes when you have complex geometries, each part of your cast have different time of solidification. So you should study for each part what is the solidification time. According to this, you will design risers, and you will put risers in zones close to the critical zones characterized by small solidification time, because in this way the riser will ensure continuous supply to these zones and will prevent blocking effects, because some other zones can solidify before. So you should be still able to reach these zones by supplying the molten metal to them. So we should locate sections of the casting with lower V/A ratios away from the riser. So freezing occurs first in these regions, and the liquid metal supply for the rest of the casting will remain open. Now also we use what we call chills. Chills are internal or external heat sinks that will cause rapid freezing in certain regions of the casting. Now we'll see what is the importance of this. Let us take the following example, okay? In the following example, we observe that if we don't do any intervention, okay, we might have, let's say, in figure A, if we put an external chill to encourage rapid freezing of the molten metal in a thin section of the casting, this will help into avoiding the formation of cavity. So here, for example, if you want to have this shape, okay, if you don't do any intervention, as I told you, you have the outer part, this limiting part here can exchange with the outer environment, okay, or with the mold here material. So here you have a possibility of loss of heat to the outer environment. This will lead to a larger, if you want, a more rapid solidification. Okay, this is why solidification will start from these zones towards the cavity. Okay, and because of this effect and because of reduction in volume, you might have formation of voids in the inner part of your cavity. To avoid this, you should encourage in this zone, which is the critical zone here, because it's not interacting a lot with the outer environment. To encourage solidification here and have it in a faster way, you can put what we call external chills. When we put chills here, they will create cooling effect close to this critical zone. And because of this cooling effect created, then you will have a loss of heat towards these external chills. Okay, and this will help you to avoid formation of cavity. This is the idea, because they will, yes?
كيف في اكزامبل للتشيلز مثلا، انه شو بيكونوا التشيلز اصولا تيعملوا لا انه فاست
التشيلز مفروض يكونوا اذا بدك فيهم يكونوا PCM مثلا في بقلبهم material at very small at very low temperatures. حيلا شيء اذا بدك مسقع، واكيد يعني مثلا بيكون عندك بالPCM بولز مثلا بيكون في بقلبهم material where you can control، يعني بتحطه على temperature كتير واطي، بيكون characterized by a let's say a small freezing temperature. اوكي ساعتها بيتحول هو بيكون بالsolid state بيكون at the solid state بس يسحب heat مثلا من هيدي البارت في يتحول لliquid state اوكي وبيكون encapsulated يعني ما بيعمل ما بيصير في leakage او شيء. So أو حيلا source تاني that can absorb heat يعني you have several possibilities to put as external chills. Okay?
Okay, thank you, doctor.
Welcome. Any other question on this? Okay. Now, as we said, whenever we want to design the riser is waste metal that is separated from the casting and remelted to make more castings. To minimize waste in the unit operation, it is desired for the volume of metal in the riser to be a minimum. Okay, and since the shape of the riser is normally designed to maximize V/A ratio, this allows the riser volume to be reduced to the minimum possible value. What we are saying here is that first, we should design the riser in a way to have large value of V/A compared to your metal in the cavity. تيكون هو solidification time تبعه higher than the solidification time of the different parts of your cavity. Okay, but also this material مفروض ما نكبر كتير إذا بدكم الفوليوم لأنه this is a waste metal يعني ما حنعوزه كله يعني بالآخر البارتي اللي حتبقى will be trimmed will be cut. So this is why because we are not this is a waste in the unit operation. Another constraint هي إنه whenever we want to design a riser, the first criteria is V/A larger than V/A of the casting part. But كمان we should have a minimum volume, يعني as minimum as possible to reduce waste. And since the shape of the riser is normally designed to maximize V/A ratio, this will allow riser volume to be reduced to minimum possible value. And when we reduce, if you want to reduce V, to have V/A larger, كمان we should reduce the lateral area accordingly. Okay, بطريقة إنه تضل V/A larger than the casting part وبنفس الوقت يكون عندنا small waste at the end. We'll do a lot of problems on riser design. Okay, so please try to go over the assignment I told you about on this chapter, and we'll correct it together hopefully on campus next week. Okay, but go over them, try to do them because this will help you into practicing before we correct them together. And you have also already available recordings for corrections of all of these problems in the YouTube playlist. Okay, any question on this before we start a new chapter? Okay, so now we'll start with chapter 8. Let me, I will stop and begin a new meeting to start a new chapter.
Doctor, I have a question.
Yeah.
هو ما كتير خصوا بالchapter.
Yes, it's fine. Tell me.
فينا نترك الchapter الجديد للمرة الجاية؟
No. يلا let us start.